In section 10, I take a look at other analysis approaches that can be applied to cross-lagged panel modeling with binary outcomes. First, we consider adding measurement error to the model. Second, we're going to look at using the observed binary y variable as a predictor instead of the latent continuous Ystar variable. And then I'm going to think about reciprocal modeling. On slide 91 then, measurement error can be added to both CLPM and RI-CLPM for categorical outcomes. And that works okay in most situations with Monte Carlo simulations. But real data is another matter. For the suicide substance abuse data, it does fit better for some of the model but fails for several other models. Now, imposing restrictions to make the model more stable is possible, like time-invariant measurement error. But that, however, does not give time-invariant reliability because of Ystar variance changing over time. And if you want to impose time-invariant reliability, you need to use parameter constraints and model constraint to impose that, and that can be complex. The topic of measurement error in these models is also covered in the Asparuhov-Mutén paper, and Tiemer calls that the MEER model, measurement error autoregressive model. It is difficult to work with in practice, even for continuous outcomes, and I think a little bit more difficult for categorical outcomes. So I generally advise to avoid that kind of modeling. On slide 92, we have another variation that's possible. If you look at this model, you have the random intercepts IY and IZ for two processes, and you note that the Y's are directly regressed onto each other. No residual autocorrelation in this model. So the cross-lagged effects are between the observed binary y variables. This is possible to do in Mplus. You work with a continuous latent Ystar model underlying this, but the relationships are really such that the predictor is binary and not the continuous latent Ystar. For one such model is drawn here then, the DRI-AR1 model for observed binary outcomes. You can do that using Bayes with the Mplus analysis option, analysis command option, predictor equals observed. It's not available for WSMV. WSMV is wholly focused on Ystars as predictors. Now for this model we don't have Bayesian PPP because we're not testing the model for the Ystars. We want to test the models for the Ys here. But we do have, of course, the frequency pattern and the bivariate table residuals that we can check significance of. Predictor equals observed is not relevant for the RI models like RI-AR1 using the residual hats variables because they are by definition latent. The predictors are latent. There is related econometric modeling that you may be interested in. In econometrics, you talk about these random intercepts, which psychologists think of as stable traits, instead as individual specific heterogeneity, individual effects. And there's an edited book called Panel Vector Autoregressions. Vector meaning, in this case, that we have a two-dimensional vector of two variables. And that's for binary data. You may want to take a look at that. They use a little bit different framework than we use here in Mplus. Now, turning to slide 93, how does this work out for the data set suicidal ideation and substance abuse? Let's first on this slide take a look at each process separately. Suicidal ideation at the top, substance abuse at the bottom. So the key models here are the AR1, AR2, and DRI-AR1 models. So we have first the new observed approach versus the latent approach that we've used so far. So the latent versions are the same as we had looked at on previous slides. So we don't have a PPP value for the observed, as I mentioned, but you can look at the response pattern and the bivariate frequency fit. And you find then that you have two significantly ill-fitting response patterns. One is for the observed frequency 155, which, as it says at the bottom here, is the most frequent pattern of zeros for suicidal ideation. So that's a bad misfit. And you have 46 cells in the bivariate tables that are have significant residuals. And we said that an acceptable level was about 6. So that's not a good model for the observed AR1 model. Now, the latent model is only slightly better, but what you really need is a lag2 model, AR2. In the observed case, that doesn't seem to help very much for the response pattern. You still have this misfit that you had for AR1. The number of bivariate cells that are significant go down from 46 to 12, so there's an improvement. But this is still not a very good model. The earlier latent model that we used before, however, has a very good fit. For the DRIAR model, adding a random intercept to the AR1 model, so you get one more parameter here, fits well for the observed approach and fits well for the latent approach as well. So there's no clear indication what to choose. Turning to substance abuse then, we again reject the AR1 model because we get poorly fitting response patterns. The most frequent one, 201, and too many significant bivariate cells. Taking the latent approach instead, we get one response pattern. That is the most frequently observed one, misfitting, but at least it's an improvement on the observed approach, but still not acceptable. So you go to AR2, and the observed improves a little bit, 10 instead of 49. It improves over the AR1 model. The latent model, however, is much better fitting and would be the one you would choose in this case. Now for the DRIAR1 model, the observed approach fits very well, but the latent approach not as well. The most frequent pattern is ill-fitting. Going to the RIAR2, the observed still fits well, but you still have a problem for the latent approach. So you get slightly different results here. Often the latent approach is better, but not always. Going to slide 94, then we have the bivariate situation. So we do the CrossLagged modeling here. And we're only focusing on these two models in this case for simplicity. The observed predictor approach fits rather well, and so does the latent. And this is true also for the RIAR12. Observed and latent both fit well. Now, how do the cross-lagged estimates differ between these two models? Well, let's look at the ones that are significant. In the observed approach, Y6 on Z5 is positive and significant. That is substance abuse at a previous year influencing suicidal ideation at the next year. Z4 on Y3, the reverse relationship, is positive and significant, and Z7 on Y6 as well. In the latent approach, we have only two of these, but the two that are significant are the same as what we found for the observed situation. It may be that we have perhaps a little bit less power in the latent approach. I don't know. I haven't done simulation studies to be able to say really. Okay, the third and last special topic then, taking a look at lagged versus contemporaneous influence for Ystar. So now we're back in the Ystar approach. We just draw the model in a simple way without the Ystars, but we know what it means. So at the top is the CrossLagged model that we have looked at, that we've used throughout so far. But you can really also consider an alternative model where you have not only these cross-lagged effects, but also contemporaneous influence, reciprocal interaction between the two variables. And the bottom model with the reciprocal interaction, that is, what you do this year influences on one variable, influences what you do this year on the other variable. Maybe more realistic, but this model is not identified without parameter restrictions. And these identification difficulties were described in this Greenberg and Kessler publication that you have in the reference list. So you may want to fit this model with all of these arrows included, but you really have to make a choice of either doing the regular cross-lagged modeling or the reciprocal modeling. Staying with the red arrows or the green arrows, some of which are in common here and become orange, but other ones that are unique to the model that are red here and green there. So you have to make a choice. And I would say that cross-lagged modeling, modeling those effects is suitable for variables referring to current status. How do you feel right now? What are you doing right now? But reciprocal effects, this model on the right, may be suitable for variables referring to past status. So take, for instance, the example of suicidal ideation and substance abuse, which refers to what you did during the last year. So the question is, if you had substance abuse when you were 20, is that what influenced suicidal ideation at age 21? Or is it more likely that substance abuse during age 21 influences age 21 suicidal ideation? I'm saying that the cross-lagged effect from 20 to 21 may be of ignorable magnitude, so we may be okay leaving out the arrows like that. Now this reciprocal model is actually identified because of the econometric rule of when you have reciprocal interaction, if each of the dependent variables has its own predictor, which they do, then the model is identified. So you have these two models, and they have the same number of parameters. Instead of the cross-lags, we have the reciprocal interaction. And for continuous variables, the two models actually fit the same. But a test of time-invariant cross-lagged effects versus time-invariant reciprocal effects gives different results. For categorical variables, the two models actually fit differently. Now, using the cross-lagged model to analyze data generated by the reciprocal model, say that the reciprocal model is the true model, well, that will show cross-lagged effects. Because if you generate data according to this model, but fit this model, then the influence from, say, this variable down by that arrow to the other variable has to go this way, because there's no effect coming this way. So you can't say that if you see significant cross-lagged effects, that means that the model on the left is right. It doesn't rule out the reciprocal model. Now, applying this reciprocal model for the suicide substance data, simulations show good performance of the model for large sample sizes, n of the order of at least 2,000. But the reciprocal AR model does not fit the suicide substance data. The reciprocal RI-AR model, which that version also is possible, fits well, but does not give believable results for the reciprocal effects and the residual covariances. I'm talking about this covariance here, with some very high correlations among the estimates. So the estimates don't seem to be clearly well defined, bordering on empirical non-identification. And the model using predictor equals observed is actually not identified. Reciprocal interaction with observed binary variables is not identified according to an old econometric text by Madala. Now, of course, there's a hybrid model here too. You can have both lagged and contemporaneous effects. So, for instance, if you have strong substantive reason for saying that if there is a contemporaneous effect, it only goes in one direction, well, then you can identify a cross-lagged effect in the other direction here. So that may be practically useful for some specific situations where you have a strong reason for the specification.